I would like to extend my power rule to include negative values for n. So far all I've got is I know that this works for positive values of n. That's the way I constructed my proof. So what I'm going to do next is I'm going to let m be a negative n, and I'm going to find the derivative using the quotient rule. So first off, what we really want is the derivative of x to the n. I could write this as derivative with respect to x of 1 over x to the negative n, and these two are equivalent. Since I know that m is negative n, I could then write this as derivative with respect to x of 1 over x to the m. Now I have a perfect setup for the quotient rule, whereby this is f and this is g. Using that quotient rule, I'm going to say I need, it is low d high, so it's x to the m times the derivative of the high. That would be a 0. That term's gone. Minus, so it's low d high minus high, that's a 1 times the derivative of the denominator. And the derivative of that denominator would then be m times x to the m minus 1 all over x to the m quantity squared. Okay, so let's see what I have here. You're gone. I have negative m x to the m minus 1 over x to the 2m. Now I can subtract exponents because I have division, so that's negative m x to the m minus 1 minus 2m is going to be negative m minus 1. Okay, so now let's replace, because I really care about this n. That's what I really wanted, and that's an n, and that's an n. So let me replace it back with what I know it is. So that's n x to the n minus 1. Voila. There it is. I have now extended it so that we can have whatever value of n that we want. So I've extended it for negative integers. Alright, let's play. I want to write this now as, because I could use the quotient rule, you're right, but I don't want to. I want to use the extended power rule, so that'll be 9x to the negative 5th. So this would be, bring this down front, negative 45. X to the negative 5 minus 1 is a negative 6. Writing in a better looking form. There we have it. Let's see, we need to use the extended power rule, so let's go ahead and bust this fraction and write it as 3t to the 10th minus 4t to the negative 6. Then I'll just do each one independently. The very first one would be 30. T to the 10 minus 1 is 9. Minus, bring down the negative 6, multiply it here. Oh, that'll make that a plus 24. T to the negative 6 minus 1 is negative 7. Putting it in a more appropriate form, 30 t to the 9th plus 24 over t to the 7th. And if I want to make it look like the problem that I was given, I could just multiply top and bottom on this first term, by t to the 7th, so I could have it all in one little chunk. So multiply this guy here by t to the 7th over t to the 7th, and I would end up with 30 t to the 16th plus 24 all over t to the 7th. We found the derivative of e to the x, but as you well know, we're not always looking at just e to the x. Sometimes we have e to some constant, and they're going to call it k times x, and eventually we'll extend this to e to some function up here. So that will come in a subsequent section. It's not right now, but we will get there, so that's not today. If I have a constant times this x, I could do a proof called mathematical induction. The easier proof would be using the chain rule. We'll do that later on, but I just kind of want to show you the concept of what's going on here. Let's just look at if we had some f of x. We're not going to do a real proof here. This is just looking at what's going on. Let's say it's e to the 2x. I could say that that's e to the x times e to the x. And if I did, I could use the product rule because I already have a proof for the product rule. So let's do f prime of x using the product rule for this particular individual case. Remember, this is not a case for the entire generality of everything. It's just a proof for, or it's just a, it will be a proof for e to the 2x, and I could extend that for 3x, 4x, and on, which would be n to the nth case, which is induction. But that would be later on. All right. So for the product rule, I take the derivative of, let's just say this is f and this is g. So I'll take the derivative, let's say f, that's e to the x, times the second one plane, that's e to the x, plus the first one plane, e to the x, times the derivative of the second one, that's e to the x. This would be e to the 2x plus e to the 2x, which in other words is 2e to the 2x, which follows what just happened here. Notice that e to the 2x, the derivative would be 2e to the 2x. Same thing if I were to go extend this to e to the 3x, I would have three things multiplied together, so I'd have to use the product rule 3 different times, and I would still get the same answer. Alright, let's find the derivative of this. Oh, this is a product rule. That's an f, and this is a g. So y prime equals, we'll take the derivative of x, that's a 1, times g just all by itself, e to the 5x, plus the f plane times the derivative of g, that would be 5e to the 5x. Cleaning it up just a hair, e to the 5x plus x, we'll say 5x e to the 5x. Okay, that is a fine answer. If you like, you could factor out e to the 5x and say that that's 1 plus 5x. That's also pretty cool looking as well. Either one of these two answers is correct. Let's go to the next one. Y prime equals, this is just a constant multiplier times this e to the kx function. So I'm going to say that it is 1,000 times 0.07 e to the 0.07x. And that gives me, move the decimal point 3 places, 70 e to the 0.07x. Done with that one. Alright, I've got a population model here. They want me to compute and graph the instantaneous growth rate. Instantaneous means I need the slope of this thing, and then slope means I need the derivative. P prime of t. I will be using the quotient rule, where that'll be my f and that'll be my g, where f is my high and g is my low. So I'll do low times the derivative of the high. That's just going to end up being 0. So I'm going to write all this stuff, and it's going to end up being multiplied by a 0 anyway, times the derivative of the high, which is 0, minus the high, which is 400, times the derivative of the low one. The 1 is gone. This is going to be 3 times the negative 0.5, so that is going to be negative 1.5 e to the negative 0.5 t. Okay, all over this 1 plus 3e to the minus 0.5 t quantity squared. Multiplying this out, I would get positive 600 e to the minus 0.5 t all over 1 plus 3 e to the minus 0.5 t quantity squared. There is my formula for the instantaneous growth rate, which they didn't write it on here, but it's graphed in red right there, or in pink, whatever you want to call it. The population is graphed here. I noticed that its highest value, let's see, its highest value looks like it's occurring somewhere in here. They tell me to use my calculator to get this. So we'll just use their handy dandy little graph. I love these things. I believe it occurs somewhere in here. You'll see that I stopped it there, right? And you'll just have to see, you can use your trace value on your calculator to see where it is that you get that highest value, that highest y value. And until we do a little bit more calculus, we won't be able to get that maximum value, but eventually we'll be able to calculate it analytically, and I know you'll be so excited about that. Now the steady state population time, that is the actual population graph, and it wants to know where is it that we think this population, what y value is it approaching. Formally, that would be the limit as my t goes to infinity of that function, which is 400 over 1 plus 3e to the minus 0.5 t. And by plugging in infinity, this guy right here is really 1 over, because it's a negative exponent, it really looks like limit as t goes to infinity of 400 over 1 plus 3 over e to the minus 0.5 t. This quantity right here, oops, not plus, it's once I put it down in the denominator it's plus. So this exponential is shooting up to infinity, which means that this term is going to 0, and then I can plug in, because it's just a constant, and there's what I get for the steady state value. So formally that's how you would get it analytically, or using your symbolic methods. Alright, this little messy guy here, I see, I'll kind of look at it as a 4x, an e to the x, and this guy down here. So I see I have a lot of stuff going on, so I'm going to look at it as the quotient rule first. This will be my f, and this will be my g. Y prime equals, let's just write it down formally. It would be g times f prime minus f times g prime all over g squared. Okay. Because I know this is going to be messy. G is x squared plus 1. F prime. Well, f prime is a product rule, so let me go get f prime. f prime is, using that product rule, it's the derivative of, we'll say the first one, so that would be derivative of 4x would be 4 times the next one plane plus 4x times the other guy plane, that would be e to the x. So there's f prime. So I'm just going to plop that down. Minus f is this 4x e to the x times g prime. G prime is just a plain old 2x all over g squared. That's x squared plus 1 quantity squared. All right, a little bit of messy stuff, a little bit of algebra to do from here. I'll write down all my terms. All right, here we go. X squared times that, that's going to be 4x squared e to the x plus 4x cubed e to the x. Okay, done with the x squared guy, plus 4 e to the x plus 4x e to the, oops, e to the x, sorry about that, chink, e to the x minus 8x squared e to the x all over x squared plus 1 quantity squared equals, do I have any like terms? Looks like this guy and this guy are like. I'm going to write the x cubed guy first though. 4x cubed e to the x. I'll write the x squared guy next. Minus 4x squared e to the x plus 4x e to the x. I like to write them in order. I'm sorry, it's very compulsive. All over x squared plus 1 quantity squared. That's a fine answer, but notice how everybody in there's got a 4 and an e to the x in them. So another compulsive thing I do is I gotta take them out. Then I get x cubed minus x squared plus x plus 1 all over x squared plus 1 quantity squared. Mentally what I do is check to see if this thing would factor, or either the numerator or the denominator would factor. If they had any common factors, I would go ahead and factor that and then do my canceling, but this does not, so I'm actually done. And I think that concludes 3.3. Ah yes, and remember, come see me and collaborate or email me if you have any questions. Be glad to help you.